Tech giants are pouring billions into designing highly specialized AI microchips, yet general-purpose GPUs still hold an iron grip on the market. The standard assumption in engineering is that as a new technology matures, the hardware running it should naturally evolve toward highly efficient, fixed-function specialization. Historically, computer scientists relied on classical Amdahl's law to model performance scaling, but that math was built for a different era, assuming a uniform grid of identical processors. A modern chip is heterogeneous, mixing flexible cores with dedicated tensor engines on one die. Inside this physical boundary, chip design is a zero-sum allocation game over a fixed budget. We define X as the specialized logic fraction, and 1 minus X as the remaining programmable compute. Because hardware scaling is now an allocation problem rather than a replication problem, predicting whether GPUs or specialized chips will win requires a completely new mathematical framework for how computational workloads behave. To solve this allocation problem, we have to throw out the old metric of measuring the parallel fraction of a workload. That concept is obsolete. We have to replace it with the metric that drives modern computing, S, the value scalable fraction. A workload is bounded if pumping more processing power into it merely gives you the same answer faster, without materially improving the actual quality of the result. Conversely, a computational stage is value scalable when additional compute actively improves the qualitative result, giving you higher fidelity, deeper reasoning, or richer generation. This creates a physical constraint on the chip. The value scalable work must remain on the programmable side of the die because it needs a flexible substrate to dynamically absorb that additional compute over time. Identifying S dictates exactly where the silicon budget must be spent to maximize the actual utility of the chip. We can see exactly how S shifts in the real world by looking at the evolution of graphics rendering. Classical graphics rasterization is highly parallel, but it is effectively value-bounded. Once you calculate the basic visibility and geometry of a scene, throwing more compute at those initial stages doesn't add much new information. Modern rendering, relying on ray tracing and neural reconstruction, is entirely different. It is intensely value scalable. This image shows the raw output of a low-sample acquisition pass. It provides the initial geometry and lighting data, but it is extremely noisy. By passing that noisy signal through late-stage neural processing, a flexible substrate extracts massive perceptual quality, creating a clean, high-fidelity final image. Mapped onto a modern rendering pipeline, early bounded acquisition stages, like primary visibility, physically shrink in runtime. Meanwhile, later stages, denoising and reconstruction, expand to consume the vast majority of the execution budget. The value scalable fraction, S, is driven sharply upward. Because the heavy lifting has moved entirely into these programmable, model-driven generation stages, building rigid, fixed-function hardware for the front end actively loses value. As a domain matures and incorporates learned models, the value-producing computation permanently migrates away from specialized pipelines and lands squarely on shared, highly programmable compute. This migration of value can be proven mathematically by optimizing the modern execution time equation. This equation calculates a chip's total execution time, T of X, based on hardware allocation between specialized and flexible logic. The crucial variable is R, representing the relative efficiency advantage of specialized hardware over programmable compute. This chart shows execution time dropping as we add specialized hardware. For low values of S, the curves form a deep U shape. The bottom is the optimal allocation point, X star, proving that dedicating silicon to specialization is highly beneficial here. But as S grows, the physical hardware requirement changes dramatically. Taking the derivative reveals a strict collapse threshold. The critical limit of S equals 1 minus 1 over R. If S equals or exceeds this threshold, the optimal amount of specialized hardware mathematically collapses to exactly 0. This race diagram plots S against R, showing the efficiency bar for a custom chip to survive. At 95% scalable, a specialized chip must be at least 20 times more efficient than a general GPU just to justify existing. Specialized architectures fail because the mathematical bar for their existence rises exponentially as AI workloads scale. This mathematical collapse perfectly maps to the central hardware debate. It explains exactly why narrow, domain-specific AI accelerators struggle to displace the GPU. AI is defined by a moving value frontier. The most critical, value-producing computation constantly relocates to new algorithms and architectures. Specialized AI accelerators can only win when the scalable fraction is small and the boundaries of the computation remain completely fixed in place. Modern AI scaling laws constantly push that scalable fraction higher. Researchers continuously introduce larger models, dynamic routing, and massive late-stage inference compute, shifting the math entirely. Google's TPUs appear to be an exception, but they survived precisely because they avoided over-specializing on a single neural network design. Instead, they moved up the abstraction ladder to target programmable, dense tensor math. A rigid hardware block is stuck in place. A programmable GPU substrate constantly improves via software updates, sparsity, and memory optimization, without requiring a billion-dollar physical silicon redesign. As long as scaling laws hold true, the supreme architectural advantage belongs to flexible systems that can relentlessly track and absorb whatever computation becomes valuable next.